In the early 1880s, Osborne Reynolds did a series of experiments on flow-through tubes and came to the conclusion that the criterion for the onset of turbulence was a dimensionless function of the flow parameters, which has since been called the Reynolds number. There is usually a certain amount of arbitrariness in the definition of a Reynolds number, but for pipe flow, let's take it as the diameter multiplied by the average speed divided by the kinematic viscosity. Although the question is still under investigation, it seems that if the Reynolds number, so defined, is appreciably less than 2,000, the fluid is not turbulent. In this experiment, we have deliberately made the input conditions somewhat abrupt. The onset of turbulence occurs at a Reynolds number not much over 2,000. However, if we improve the entrance conditions by putting a nicely flared funnel at the upstream end, we can delay the transition to turbulence to a much higher Reynolds number. Now we have increased the flow rate and further decreased the viscosity. With very great care, it is possible to push the Reynolds number up as high as nearly 100,000 without turbulence. However, here we can reach only about 8,000. The onset of turbulence depends upon the growth of perturbations because of an instability. For example, at this Reynolds number, the flow alternates between laminar and turbulent modes, apparently randomly, depending, presumably, on some random variations of the perturbations. Prominent in our defining syndrome was the word mixing. What about mixing? Let's modify our experiment by introducing a thin streamer of dye into the flow. Notice that the dye forms a thin filament which maintains its identity with very little change right down the tube. The only mixing is molecular, and the concentration gradients are so small that this process is very slow. This is laminar flow. Now we increase the Reynolds number. At the onset of turbulence, our dye filament seems to explode, and the dye is rapidly mixed across the tube. If we want to, we can regard the increase in pressure difference as a manifestation of mixing too. Mixing of momentum. In laminar pipe flow, the velocity profile is parabolic. Near the walls, there is a considerable quantity of relatively slowly moving fluid. Dye, injected near the wall, marks some slowly moving fluid. When it leaves the pipe, it falls with a steep trajectory. Notice that the slowly moving fluid near the top of the pipe also falls steeply. The rapidly moving fluid from the middle of the tube falls with a flat trajectory. Compared with laminar flow, in turbulent flow, the mixing of momentum causes the velocity to be much more nearly uniform. The fastest fluid is not quite so fast, and there is very little slowly moving fluid. What little there is can be dragged along with the rest when it leaves the pipe. Nevertheless, the velocity must vanish at the wall, so we can regard the wall as a sink for momentum. Turbulence increases the rate at which momentum is transferred toward the wall. Thus, with turbulence, we need a larger pressure gradient to replace the momentum lost to the wall. Although the principal motion of these bubble patches is downstream, there is a very appreciable cross-stream component. Fluid moving across the stream in this way tends to carry its properties with it. It is these cross-stream velocities which do the mixing. For example, the momentum close to the wall is appreciably less than that in the center of the stream. cross-stream motion carries low momentum fluid into the center of the stream and high momentum fluid toward the wall. Thus, the turbulence transports momentum. In this shot of the Fraser River at Hell's Gate, we can see great volumes of slow-moving fluid which come up from near the bottom and very much reduce the average speed of the surface flow. Turbulence can transport more than momentum. With scalars, such as dye and heat, mixing may be primarily a matter of stirring a fluid which is already grossly homogeneous. On the other hand, if we have a mean property gradient, the most important effect of the mixing may be a transport of some property, as dye is transported across this channel. The wall here has been deliberately roughened in order to increase the ratio of turbulent to mean flow speeds. The dye also helps us examine the velocity field. The blue dye is injected at the center of the channel where the flow is fastest. The red dye is injected near the wall into the slowly moving fluid. Notice how, even at the same distance from the wall, the filaments of blue dye move more rapidly than do the red dye filaments. The forward momentum of fluid moving towards the wall is on the average greater than that of fluid moving away from the wall. The region near the wall, then, continuously gains momentum at the expense of the region near the center of the flow. Since rate of change of momentum is force, and force per unit area is stress, we see that the presence of the turbulence produces a stress, the Reynolds stress, within the fluid. The Reynolds stress is additional to the ordinary viscous shearing stress and produces the increase in drag, which we found in our pipe flow when it became turbulent.